Hey everyone, today's presentation is about what I call complexity decay that my algorithm G3S is capable of. You've probably already seen on q-dss website the snapshot of this particular file. And the numbers here representing particular formulas split into batches. So batch A of a CNF formula containing 4,000 variables and over 14,000 clauses. The batch B multiplied by 10, which is 40,000 variables with 144,000 clauses. And again multiplied by 10, the batch C, and up to 4 million variables and over 14 million clauses for the batch D. And as you can see, the wall time, the raw time basically of each run goes from a few seconds, which is an average of 16 seconds, as I can see in my Excel spreadsheet, going upwards to 290, almost 300 seconds, then upwards again to 4,500, and up to a day per execution. Now, the order of complexity for each run, though, decreases from batch to batch, and that's very interesting. That's the interesting part. It decays. The order of complexity decays, goes down. And from the first batch, which took the order of 2.44 in average, down to 2.2 almost, and even lower to n square, sorry, and down to under n square for the last batch. And that's spectacular. Why? Because at some point, after a certain number of batches, while increasing tenfold the number of variables, G3S will probably need only one pass through all the variables, so O of n, order of n in execution time, to reach a result, to find the solution, if any. Now, when this will happen, let's assume that the slope here represents exactly what we need to see. Basically, will help us bring some conclusion on this. Let me explain you what this represents. On the right-hand side, it's the Y scale for the execution complexity, the results of execution complexity, and that's this one. And then on the left-hand side, the y-axis, we have the logarithm of number of variables in each in each batch file. So this is batch A, batch B, batch C, and batch D. And the trend slope, the linear trend slope, will help us figure out when this linear run will happen eventually. So since x represents the number of samples, let's see how many extra samples we will need to reach y equals 1. So considering y equals 1, then it's easy to compute the rest of it. It's so x is 1.486 divided by 0.171. Okay, so roughly in 90 samples, we should reach a linear run, linear complexity run. 90 samples, that is 50 more. Basically, that should increase that many times the number of variables, reaching 10 to roughly 11. So let's consider 10 to 11 variables. And that's humongous number of variables. It's a humongous formula, very, very complex formula. And I'm pretty sure nobody did reach that so far, not even 1 billion variables in a formula. But I am very hopeful that soon G3S will be able to do that. Now, while this has been recorded, also the run itself has been recorded. So this is the batch that I was talking about. That's from the first batch, batch A, with 4,000 variables and 14,000 clauses. And since this is a very big one, I opened it before the recorder, before I started the recorder. So this one has 4 million variables and over 14 million clauses. And I also recorded back in February this year. So let's watch how this run happened, actually, where the numbers are coming from. And since the run took overall about a week, I recorded it by stop and go of the recorder, because nobody wants to sit in front of the video for a week and watch numbers scrolling on the screen. So that is started, the run has started on the 20th of February and took, as I said, about a week. But you see where the numbers in the spreadsheets are coming from. The first batch, the batch A, is done, actually pretty quick. Batch B, the same, actually. The run started at 9:40, as 9:40, I think. Yeah, 9:40 a.m. and has been done in less than an hour. So 10 formulae of 40,000 variables each. And then the next run of 400,000 variables took a bit longer, about an hour or so per formula, but still very decent. At the same time, the order of complexity is dropping, as you can see. Now, the batch D started, the big one was 4 million variables each, and those took almost a day each. Almost a day. And that was a very long run. So that being said, I will stop the recording I did back then and continue the discussion around the results. So I've done this with actually several types of formulae. So batch 40 is the one that we saw before. Then batch 2.8, or 28, that's going from 2,000 variables up to 2.8 million. And the second screenshot on that, on my website, on the q-dss website, representing the numbers from that particular batch. Now, the question is, how is G3S doing, achieving such a performance? So, without going into very deep technical details, I would say the way to achieve this is by using the similarities, the patterns, basically, between batch files. As you can see, the clauses versus variables ratio is kept constant. So G3S, using its artificial intelligence and a little bit out of its genetic algorithm, is using this in order to improve the performance from batch to batch. So if you look at the complexity here, let's say 2.52 for n variables, that means if n 2,800 variables power 2.52, that means the algorithm needed for 400 and almost 500 million touches of a variable in that formula. What if this complexity, 2.5, would have been kept for the next batch, the 28,000? That would have been 28,000 to the 2.5. And you will see that my algorithm is supposed to have 132, what is that, billion hits. And it's not really feasible since my current computer can only do 40 million hits a second. So let's divide this by 40 million and see how many seconds would have needed. 3,000 just for the next batch. So over 10 times more than it did actually. So let's go to the next batch and see even a bigger difference if the complexity would have been kept around order of 2.5. So that would be 280,000 variables power 2.5 roughly. That is a much bigger number. It's 41,000 billion hits and divided by 40 million. 40 million hits per second that my computer is able to do would have taken me about 1,000,000 seconds. Well, it didn't. It only did like 2,000 seconds. And if we divide this by 3,600 and to figure out how many hours, supposed to take 288 hours on a polynomial run of n to the 2.5, which obviously didn't happen. If we go to the other one, those number will be evidently even larger. So that being said, the performance of G3S becomes obvious, and that is, I hope everybody who understands the non-deterministic polynomial complexity knows that this is very hard to achieve, but G3S does it. And not using any spectacular piece of hardware, but an i7, let me show you what I'm using, is an i7 Intel core with 16 cores. So that is about the complexity decay. And I'm expecting a lot of questions regarding this because I consider it spectacular. So waiting for question. Until then, stay safe and goodbye.